on the model performance. So once we have done with training the model, we must work how it performs. So we use our precision. We use our precision for okay. Sorry. Okay, so we use our precision, recall, and AMP at 50 and APA at 50 to 90. So result. So our precision, when we say precision, we mean like the actual predicted value that the model has predicted. So as we see, 81.6%, it means the model performed very well. It predicts more than 80% of corrected leakage. So we have recall. When we say recall, we have how does the model predict the actual leak, the actual pipeline leak? So we have an MAP, which is mean average precision. So we also use it maybe to know how the predicted value that's predicted by model and actual value. So here we give the model once you don't assure that it's not 50% probability, so you can just escape it. So here we use 50 to 95%. We start with 50, then 55, then 95 rest. And this is good number for model. Then we have MAP as well 50, which is what it's exactly from 50 to above. Then we develop a software with in place of, like, say, camera. Since we don't have camera, so we have to develop a software that will text our model to see. So what you do is just upload the picture there. Once you upload, just click and you see the result. Here is what input, while the other side is what output. So we use the B11 model and generative AI. So once you upload the picture here, as you can see, once you upload it, so it will work.
1 minute more.
Also, once you upload your pipeline, whether it has a ticket or not, it will output the result. And here you will see the percentage. So maybe it is some problem, it will detect that gas that they are at 95%. So here is the corrective action that's generated by AI generated. So just relevant and just relevant cost-effective monitoring to help in human risks, like in the case of hazardous inspection. We have to improve accuracy in that. This will really improve
time up. Time. Thank you. Can we appreciate them, please? Over to the judges.
Thank you for the presentation. My question would be, the first question would be, what data did you use to train the model? And the second one is, how are you going to be acquiring the images for the pipes? What's the practical way?
Okay, from the methodology, we found this data from RoboFlow, the software that we normally use to upload maybe open source data. So we use a mixture of real-time pipe image that has maybe leakage, and also the one that is off. So we use the one. So we use the 3,506 image, the one that has gas leakage, and the one that has water leakage, and the one that doesn't come. So we use to train the model. And where we get data is by taking the image from maybe process close station or refineries, and come and train the model.
Find out how will it be applied practically?
Okay, so actually you have to integrate it to a drone or fixed camera. So once because of maybe the financial constraints that stop us to do that. So we don't act like a service company. So if you have like drone, you can maybe ask us and we will provide API for you to mod the model in your device. That's how we can apply it together.
Thank you very much for the wonderful presentation. And just to correct, Mr. Wanobi, I don't think he spent his up to 1 minute during his presentation. So just if it's 1 minute, let's give them 1 minute so that they can complete their presentation. Thank you. My question is, first is your data collection. I think almost the same question. Your data collection architectural design. I'm not seeing it. Your topic is leak detection. How do you detect the leakage from the pipeline? I'm not seeing your sensors. I'm not seeing your IoT. I'm not seeing your, I only see the software interface, but I'm not seeing the hardware interface. So what's the relationship between the hardware and the software? And how do you link it with your software you develop?
Okay,
Which language do you use to develop your software?
Thank you for this question. The reason why we use our website is because there's absence of hardware. We don't have the money to purchase hardware to mod the model, that's why. So normally, once we develop our model, we have to integrate it into drone or Internet of Things. And Internet of Things must have maybe the camera. Let's say maybe this camera or drone. So we just mod our model into that drone, and the drone will capture the image. Once the drone has captured, so the model will process and give the output, which will generate the practical action.
But if I don't want to use a drone, what do? I have a pipeline. I can use my sensor. You saw the other guys did presentation similar to this. Now the other sensors I can also use too.
This year the B11 is more important.
What is it?
To be an image for it to be able to work. So it takes image data set.
She was asking how do you train your model?
Okay.
Your B11 is a machine learning algorithm.
Yes.
True.
Okay.
Then now how do you train your model?
Yeah. So as you said before, we collect our data and then we annotate them. Like
where do you collect the data from?
Also, the other method is we can get images from maybe from what is the road license. So what we need to first do is we need to annotate the image so that to show you that if he sees this, it's a leak. If he sees this, it's not a leak. So that it will not confuse leak with maybe dust or maybe let's say dust or maybe
So how much did you spend in developing this project? Did you spend money? You don't need money then?
I need money for hardware.
You didn't tell us how much you need. I want to give you money and you come to me that you don't need money.
No, there are a lot of data that is developing and
it's still a concept. That means I should go back with my money.
no.
What's your economic value?
Okay, then and apart of this open source data set, we can also collect local data from environment around Africa, like from refinery and fuel station. Maybe when we have a incident of gas, we can maybe take the picture and what's going on.
You're looking at data set, you're looking at drone, capturing pictures and images. They are not relating at all. Yes. I don't know, I will just speak to my brother and continue.
So a very quick one. Your RoboFlow data, was it annotated or you guys annotated it?
Okay, RoboFlow, we annotate some and some.
What percentage of that data did you use for training and what percentage did you use for testing?
Okay, we use
Okay, there is charge actually. Yeah, it's always like anyway. 21.
For testing. Okay, by
Thank you very much. Can we appreciate them on stage, please? Line University is next. Please, 2 minutes for setup. Unipod, get ready. I think you're about to start. Okay, over to you. You can start. Thank you.
According to the Global Energy Monitor, 50% of oil spills are due to pipeline leaks.
The Trans-Niger pipeline, which is a key offshore pipeline, has a capacity of over 180,000 barrels of crude oil daily. This illustrates the enormous risk if any leak occurs.
Research shows that exposure to oil spills in region can double neonatal mortality rates, increasing it by up to 38.3 deaths per 1,000 live births. Why did we give these facts? My name is Daniel Adewale Balogun. And this is the design and implementation of autonomous underwater vehicles for subsea pipeline inspection. Energy. It starts with energy. Although the world is transitioning into renewable energy, 50% of our energy is still gotten from hydrocarbon. There are many ways to transport this hydrocarbon, but the safest and most economical way is pipelines. Many studies are focused on onshore pipelines, even at this event, but this study focuses on offshore pipelines. Offshore pipelines like the 1P, with depths of 30 to 75 meters. Offshore pipelines like airworks, with depths of up to 40 meters. But these pipelines are not perfect. They come with problems. Problems such as corrosion, material-related damage, construction-related damage, and even third-party interference. This problem leads to something we call
leaks. Pipeline leak detection has been done before. Traditionally, we use pressure sensors, and as demonstrated in this event, these pressure sensors are placed within intervals in the pipeline. When pressure fluctuates erratically, it indicates that there is a leak at a certain interval within that pipeline. But the fundamental problem with this is that the exact leak location is undefined. For onshore pipelines, we use numerous methods of finding leak location. But for offshore pipelines, autonomous underwater vehicles are used. Autonomous underwater vehicles are self-operated underwater robots. These robots use acoustic technologies, which are significantly expensive. They use Doppler velocity logs and sonar technologies. And just these two components could cost over $16,000, which is above 25 million naira. A complete AUV, like the blue robotic AUV, are the turbine, which are used to propel the AUV. The fabrication. We use two main mechanisms for fabrication. We use 3D printing and CNC. CNC stands for computer numerical control, where you use a computer algorithm to make precise cuts on metal. We did this in the fabrication lab donated by France in Now University. This is part of the AUV after resurface. Thank you.
Over to the judges.
Okay,
Good presentation. Let me say something. I like practical. If I drop this thing in a small stream, I would love to see a video. I'm struggling to understand. I'm seeing software design. I can do this now. This packaging, I can package this now. Just give me 5 hours, I'll package this now. If I drop this thing, really don't bad. Let's see a video. See this video. No. This is our brother here. This guy. This is your uncle. Just demonstrate. Let me see it underwater. Let it go underwater. I don't want to go underwater. No. You cannot bring a baby and tell me that this baby, the mother is not around to breastfeed the baby. No. Let me see it underwater. Here, this is your topic. Still underwater. What's the topic again? Underwater, isn't it? Let this thing go underwater. Let's see. No.
If we have
No, I would love to see a video. I want to see this your mechanical device underwater.
like we currently don't have a video for it. But we can.
Yeah. Have you tested it underwater? God bless you. Have you tested it underwater?
Yes.
Let me see a video or a picture. I hope I'll not go and bring it back again.
Okay, we're here to see creative innovations, practically demonstrated. So that's why you see some of the judges are pointing on that. So whatever you've dealt after the boss and all that, let's see what you've done. Thank you. Yes.
Thank you for your demonstration. Team University. If you intend to use this in Nigeria, maybe to detect leakages from our pipeline. I like that you mentioned Trans-Niger pipeline. But problem pipeline is the Transportados pipeline, what have you. Those are located swamp locations, all right? Even though they are submerged. Can we use this in such locations? You know, the practice now is we use A-frames whenever we have leakages and raise the pipeline. But with something like this, we can deploy it. So can it be used? Remember, the water is not clear. It's muddy water. Can it work there?
Okay, as I explained earlier, I use images from a vast amount of sources. These images cover different turbidity levels for it to be able to have a robust detection system. So I've tried as much as possible to cover the span of possible things that the AUV can see in an actual scenario.
I'm just trying to understand your topic. Underwater vehicle for subsea pipeline.
Autonomous underwater vehicle.
Okay, when it gets underwater, what does it do for the subsea pipeline? Does it detect leakage?
So first, what makes our whole project novel is that we incorporate machine vision with so many aspects. At first, it can go underwater and do pipeline tracking. So it keeps on course and follows the pipeline. And apart from that, it could also do obstacle avoidance. When it sees any obstacle, it could maneuver and by itself with no control. Nobody is controlling it. And apart from that, it also uses what we call visual slam odometry. So most AUVs that currently do exist have like crazy technologies that estimate their velocity and distance. And based on our research, like we haven't found an AUV that is in production that uses this virtual slam odometry, which uses its camera vision and calculates how long it has traveled and estimates, okay, this is where I am in real time, and this is how far I've covered, and this is my velocity. Then, apart from that,
there's no cost. Can I see your cost? Your economic analysis. Your economic analysis.
okay, so we put the cost to manufacture and the cost for the main elements of the AUV in traditional AUVs. So it's manufactured at $2,000, and even if sold at $10,000, brings a 400% return on investment.
So just, I don't know, I'm still struggling with your call, but my issue is we will engage after this program. If I see this in a small stream in a bucket, let me see if it's going to obey the law of flotation first.
Mm-hmm.
And let's bring in our engineering. I'm not after a good project, very good project, good business. Let me see that the mechanical device is working.
Okay,
because now, if I have a baby now and I bring my baby in and I say, please, your baby shouting, let's call the mother. It makes no sense to me. That's true.
Mm-hmm.
Thank you very much.
Okay, I have one more thing to add. He missed out something. Although our AUV is tracking underwater, it tracks at the surface because we have GPS. We cannot implement that GPS underwater. So underwater, we allow it to do what it can do. We cannot communicate with it. But at the surface, surveillance. Yes, sir, I assure you it goes underwater. Yes, sir, you can put it underwater.
Yeah.
Okay. But there is one thing about that. We came here with a plane. The batteries are not allowed on the plane. So we came here with a power supply that we can plug on the wall instead of the battery hole. Here. So once we put it in, we need to raise this part out of the water so that the water wouldn't get to touch part of the AUV for it to be good. But normally everything can go underwater. But for this point now, not everything can go underwater. And implementation. We give it results from implementation and
thank you. We appreciate that, please. Thanks so much. University of Port Harcourt. Uniport, 2 minutes for setup. We have just one last school presenting, which is New York. After that, we'll start the Presto Bowl semi-final immediately. So stay tuned and don't leave the hall. Unipo, can you start now? Okay, your time starts now, Unipo.
Good day, ladies and gentlemen, my esteemed judges and the audience. My name is Briggs Lulu, and my co-energy challenge presenter is Praise God Enuge. We are from the University of Port Harcourt, and we're here to present our innovative solution to the energy challenge titled the Heat Harvesting Energy System, a Thermoelectric Power Solution. This is our presentation outline. We move down from introduction to conclusion. Introduction. Currently, many African and non-African countries faces energy crisis. Why is this? Because currently the demand for energy is not equivalent to the supply. So that is a problem. That including my country, Nigeria. Nigeria faced in the year 2024 4,000 hours of blackout. In addition to that, Nigeria faced 230 blackouts per annum in the last 14 years. In addition to that, there's a mass untapped heat energy being wasted per annum from average household and average industry. From the chart, you can see in the year 2023, over 1.2 terajoules of heat is being wasted. Also, over 8.7 terajoules of heat is being wasted from an average industry. That leads us to our problem statement, which is underutilized energy sources and opportunities. Now with that, our aim is utilizing the heat energy sources to add to the available energy sources. I'm not saying we are replacing the current energy sources. We are not doing that. We are adding to the available energy sources. This is our idea. The idea behind our solution utilizes the Seebeck law, which was discovered by the German scientist Thomas Seebeck in the year 1802, and the law states that whenever there's a temperature difference between two dissimilar semiconductor, an electromotive force is being produced. Now, with that in mind, the major component of our prototype is the TEG, which is a thermoelectric generator. Now, the TEG, what's the principle and design of the TEG? The TEG has the N-type and P-type semiconductor. When the N-type semiconductor is being agitated with heat, the electron semiconductor is moved to the P-type semiconductor. In the same way, the Cold effect, because we have to have a temperature difference electromotive force which powers our device. Now, this is how the system works. The TEG, we have the heat source, and we have the coolant. So once there's temperature gradient, an electromotive force is being produced, which is being passed to the voltage booster and passed to the voltage regulator and passed to the voltage display to notify the user the current voltage being generated, which is then passed as an output. Now, in summary, our solution, one of our novelty, before my other speaker will talk about more, is our solution, the cold side. We are able to integrate the heat sink and water together to increase the efficiency of thermal dispersion, thereby increasing the output of our prototype. So thank you. I'm moving on to the next speaker.
Okay, my name is Unibe Fraser, and quickly we'll be looking at the engineering principles that give led to this design. So first we have our Fourier's law, which is our heat transfer, and then our thermoelectric generator, which has built with bismuth telluride, is usually of 1.5 watts per meters Kelvin. And since we're using candlesticks, the area in contact with the heat is about 0.01 meters square. And then since we use water in this scenario as the coolant, we decided to we know that water boils at 100 degrees centigrade above sea level, and then we use the temperature differential across 90 degrees so as to maximize our temperature differential. And then the diameter of our thermoelectric generator is 0.5 centimeter. Converted to meters, that's 0.05 meters. Now, in calculation, the heat transfer is about 270 joules per second. Now, power output, as you know, is P equals to IV. Juxtaposing that, we have P equals to V square over R. Now, we had our V booster, which was rated 5 ohms, is 5 square divided by 7, which was the load of the LED. We then had a power generated of 3.6 watts. Now, speaking of Seebeck effect, we used 2 thermoelectric generator, and from the specifications, we had its Seebeck coefficient of 200 times 10 to the power minus 6 volts per Kelvin. And multiplied by the temperature gradient, as I explained here, we have 0.036 volts, which is being picked up. Now, in return for this, the efficiency of the prototype is 3.6 watts divided by 40 watts, which is generated by an average candle, which can be confirmed by the audience. Then we have our efficiency of about 9%. You may say that's low, but statistically, most industrial waste converters are between 2 to 10%. And the first law of thermodynamics simply makes us understand that heat energy can not be created or destroyed, but can be transformed from one form to another. Now, moving forward, our cost analysis, we have the thermoelectric generator we purchased for about 16,000 with a list of other things, costing us about 32,000 naira. The average power generator is 3.6 watts, average quantity of heat input 40 joules. Then we decided to program our results with 50 TEGs, 15 TEGs, and 2 TEGs. You could see the power generated against temperature differential. Also, the current against temperature differential and voltage against temperature differential follows the same trend as you can see. Now, the scalability of this prototype can be seen in application to a gas flaring stack during technical flaring. Also, it can also be applied to a heat emitting pipeline, because in our design, we integrated the heat sink directly to the thermoelectric generator, making it easy and compact. And it also can be applied to heat outlets in iron and steel industry. And you may ask, why would happen to this water if water is being used? We would say in this event, the water can be used also for the cooling of the cast irons being used for manufacture. Finally, we have the conclusion. Our technology is seamlessly integrated into oil and gas industry. It aligns with the Sustainable Development Goal 7, affordable and clean energy. It is renewable and convert wasted heat energy into electricity. Now, this is the prototype. Can you please? Okay, this is all set to go. Okay, this is heat source, just like it says, being added to the tag. Now you can see the voltage being picked up. Now we removed it so as to show that when the heat source is hot, Seebeck law is being obeyed. You can see the voltage drop simultaneously, and then we decided to add the heat source back. You can see the increase in temperature going to about 3 volts plus, and then we use the power generated to light the bulb. Thank you.
Thank you so much. Good presentation. Innovation leads. Over to the judges.
Good presentation and good idea as well. So my question would be, so for this application, what would the maximum energy it can sort of produce? So I'm looking at the application, at the applications that this generator can provide. Then you mentioned the heat sources. So for me, I'm looking at also maybe practical. So you mentioned oil and gas. So in oil and gas, they kind of have generators or turbines based on maybe the gas they produce internally. So I'm looking at other applications of this generator. Thank you.
Okay, so for the maximum heat generated, for us, maximum power generated, our power is gotten as a result of the heat source. So in the event that you have a greater, much more efficient, advanced semiconductors, your power rating increases simultaneously as shown. With the multitude of the TEGs, you're able to recover much wasted heat. It can power any, basically, you could see from the slide, it could power auxiliary equipment, just like for instance, I mentioned things like their sensors and the rest. In remote regions, this is applicable because you may not be able to transmit power to such remote regions. By using this, although this is not necessarily the internal components are here, by using it and wrapping it around the pipeline, you could then use it to actually power those micro sensors which can send back other information needed without actually, while reducing your cost for power.
Thank you for the enjoyable presentation and covering all the key elements within the time frame. So I have a particular question. This has to just build on the co-judge's question earlier on. So, if you use this application, for example, in the application for gas flaring, what's the maximum heat that an equipment like this can take? Would there be need for heat adjustment? How does that impact on the cost of the equipment?
Okay, so we did a little research. Although we're not able to obtain silicon carbide, which is the most advanced semiconductor to be applicable in this case, it can withstand temperatures of 1,532 degrees Fahrenheit, which is far above what your standard technical flaring, because we don't want to encourage flaring of gases. We want to encourage a system whereby you want to flare your gas, but in the event that it's due to overcompression, we want to also see that that energy is not being wasted. Now, when you apply that to this, you will see that we could use the energy generated to power microsensors, the lighting, and also as a dual advantage, the water system or the coolant up there can also be heated. In the process of heating, that same water can also be used for injection into the well.
Did you consider the different applications? So, for example, if you're applying it to oil and gas, as we said earlier, it will be totally different when you are applying it in remote areas where there is challenge of electricity, for example. So, what would be the cost implication when you're applying it in that smaller scale compared to, the larger application, like for gas flaring or using glass flaring, for example?
Okay, we use very base and very cost effective. As there's a temperature differential, this is able to power microsensors and the rest. It generates about 3.6 watts, as you can see, the average generated watts. So that's the average power generated for this prototype. So with better advancement and investment, we can produce better equipment. Thank you.
Okay, very nice work. And I like the fact that you went into the fine details of the engineering. I like to know if you also consider the implication of much higher temperatures, because then your system would start to heat up and you need to introduce some sort of coolant. So even for something as little as technical gas flaring, how do you intend to address the issue of overheating?
Okay, the issue of overheating, in your TEG, you have the hot and the cold side. So what I feel and I believe is the novelty of this is our TEG, the cold part is seamlessly integrated to the heatsink. You could come look inside and you'll see it. And the water, simultaneously, the water helps you cool down this part as a result of transfer of heat. And then the power is generated as a result of the temperature differential. Now, just like related to what she asked, when we have better advanced equipment which we're not able to purchase due to how the high cost of it, you could use this in silicon carbide, you have carbide manganese. Those equipments can withstand high temperatures, and with our water coolant, you have no wasted energy. Thank you.
Thank you so much. Thank you so much. Can we please appreciate them on the little stage? University of Uyo, you are next. Can you proceed please to the stage? Unio. 2 minutes for setup, please. You done with the setup?
Right, good afternoon to everyone. Standing on existing protocols. My name is Living for the Light of Young from the University of York, and I am here with
We are John Edits, hailing from the Department of Ecology, University of York, and would like to actually a very innovative and groundbreaking topic that talks about innovative zero carbon methane production, integrating genetic engineering and advanced extraction technologies for sustainable methane production. All right, next slide, please.
All right, the methane. We all know that methane, a crucial component of natural gas, plays a very pivotal role in global energy supply. However, the conventional method of methane production and utilization is often associated with the release of large amount of carbon, leading to global warming and climate change. So now this proposed project, seeks to address these environmental challenges while producing methane and with a zero carbon methane blueprint. So now we are looking at an overview of the entire work. And this overview of the entire work focuses on zero carbon methane production by using advanced biotechnological and engineering solutions. And you may ask a question, what are you trying to tell me about? And now we look at that the sole aim of this work is to achieve sustainable methane production with zero carbon emission, minimal environmental impact. That is why we use genetic modification of Synegochus elongatus, PCC 7002 culture, and carbon capture and utilization technologies. And now we look at the existing technologies. These are the existing technologies of producing zero carbon methane. And now we look at the statement of the problem, which has to do with carbon capture complexities, high cost, technical complexity, high energy requirement, limited scalability, economic feasibility, and the like. And we look at our innovative zero carbon methane solution. And we look at reduction, what it tries to do. One is reduction of greenhouse gas emissions, utilization of carbon dioxide as a feedstock, production of high purity methane, sustainable and renewable methane production, enhanced photosynthetic efficiency through genetic engineering. And the last one, economic viability and minimal environmental impact. And now a good question is, how do you want to achieve this? And now this leads us to the next slide. And the next slide is the proposed solution. We look at a 3D conceptual model of the entire work. Now a good question is being asked, how do you tend to achieve this? The methodology here makes use of a lot of processes. We look at photobioreactor systems, that is biological conversions. And now we also look at methane oxidation. We also look at catalytic conversion. But now, if we look at the previous technologies that are in existence for producing zero carbon methane, we can see that we now integrate these technologies in order to provide solution and reduce carbon emissions. And now we actually tried this out with gas, natural gas. In retrospect, that is what we are looking at. So now this is the 3D conceptual model of how the entire work will be. And now the next slide shows an animation of how the entire work is. Now how the gas will flow to the Synegochus elongatus to the photobioreactor and the entire system. I will make a clarity on the microorganism we are using and why we are making use of that microorganism. Now Please pause the video, please. Thank you. Now, the microorganism we are using, Synechococcus elongatus, is actually the microorganism that is used for carbon capture, utilization, and storage. But now I ask myself a question: why is it that you allow carbon dioxide to escape out of the system before you now capture carbon? It's a good question. Just imagine I'm looking for a lion and I want to get a lion. What I need from the lion is the hide and the skin of the lion. And all of a sudden I let the lion out of the zoo, and the lion goes into the environment, mauls people, causes havoc, and then I get to capture the lion and then to make use of the lion. That is a question for sober reflection. But now if we bring it to this context, carbon dioxide is that lion. Why can't we deal with this carbon dioxide in a closed loop system without allowing carbon dioxide to get out from the system? I think that will save us a lot of stress. So this is please play the video. Alright, now this is how the system is. The system, the detailed design animation of the system. The system, various system components. And now, we look at the natural gas input. If you can look, you will see natural gas flow here to the methane oxidation chamber, whereby it is oxidized to carbon dioxide and water, and then to the photobioreactor, whereby our organism, which naturally takes in carbon dioxide. But now, since we have genetically modified it, it now operates as a methanotroph to be able to utilize the oxidized state and produce methane. Now we see the process move, and now this is the impurity removal system. Now there is a flow to the impurity removal system, whereby we make use of various seed technologies in order to be able to ensure that our methane produced is high purity, and then we get to the compressed gas storage. And now this is the physics and behind the entire work. Now we look at natural gas chemistry, methane oxidation and conversion, biological strategies, the pathways that we use and everything. We look at the photobioreactor physics. We look at the conventional purification processes, the catalytic conversion, purification technologies, and the system principles, as well as the process simulation. Our work was not, we couldn't make a prototype due to economic constraints and the stress of trying to modify the microorganism. So now we simulated the entire work using MATLAB Simulink. And we looked at an initial methane natural gas input of 100 cubic meter. And at the end of the day, with conversion efficiency of 90%, photobioreactor efficiency of 85%, and catalytic conversion efficiency of 95%,
1 minute more,
and everything, we were able to have a final output of 71.53 cubic meter of methane. Now we get to the economic analysis.
So for the economic analysis, the world today is trying to actually cut down carbon emission by 2050 to, let's say, 50% or more, let's say 100%, with companies trying to contribute into it. And we're looking at the economic analysis using our own prototype. We estimated everything to have a cost of about $238. It's basically an estimated range of $238 to about $378. And if a company is to adopt this into their system, they will have to, it will have a cost of over 17.3 to over 28.55 billion naira. And the cost analysis for this, if you will be using our own model, you will be spending nothing less than 17.3 to over 28.55 million naira to actually deal with greenhouse gas emission. And if you'll be looking at other statements, definitely you will spend more. So
time up. Can we appreciate them, please?
Thank you.
George, over to you, please.
Sorry, just a very simple question. Thanks for the presentation. What's the yardstick of calculation? The previous slide before you ended your presentation.
All right, we made use of the efficiencies.
Sorry, let me finish first. Comparing it across the various technology. So what's the yardstick for your own technology analysis, because of economic analysis?
All right. All right. The yardstick for the economic analysis, we went to verified sites And we went to some company databases to check this technology, some companies who are actually working on these technologies, to be able to see the cost of these technologies that they employ. Okay, now we are looking at, now we are making cost analysis with other technologies. Now, our technology now incorporates most of the mechanisms that are used in this technology. So these are other technology of producing zero carbon methane. And now, like this synthetic methane production tries to produce methane through carbon dioxide and hydrogen. And the same thing with the biological methanation, whereby they make use of microorganisms. And the same green hydrogen, the same thing from renewable energy and carbon capture, direct carbon capture. And the same thing with renewable electricity through power sabotage process. But now we are incorporating these mechanisms because all these mechanisms, they produce zero carbon methane. But at the end of the day, they still produce methane. So now what we are trying to do is to incorporate this technology in a closed loop so that our carbon dioxide will not escape from the system. Like now, looking at our technology now makes use of biological methods and still makes use of the sabotage process. It is in such a way that our technology is in such a way that if they...
Sorry, we just have less than 5 minutes to close the section. Our technology, can we see the technology?
Okay, so because of financial constraints, we were unable to actually make a proper prototype to actually bring down here. So what we did was that we had to put up a 3D modeling of the whole system, which was what we presented on the animation. That wasn't just an animation, that was a 3D prototype, all right, of what we wanted to actually do. Is that it uses genetic modified engineered organisms. These are the basic things we see around ourselves. It's called blue-to-green algae. They are basically the things we see around buildings that are a bit, being notched up, that have stayed for a long time exposed to let's say to the environment, cold and weather conditions. All right. So when these organisms are being conditioned, when these organisms are actually being conditioned, they can actually be a good way of trapping this CO2 from your well without taking them out first before you get them using CCUS and other tools like that. Thank you.
I like your energy and your enthusiasm and your ability to speak at such a speed where it's quite difficult for me, zero carbon fuels, there is carbon capture, utilization, storage, etc. And simulation and conceptual model and all of that. So I appreciate the fact that you noted that for certain reasons you were only able to do simulation, which is great. But I think, and this may not be a question, might just be a comment that you might want to take home. I think that when you say that, so based on your presentation, I think what it implies is that you are saying probably you have one way of capturing carbon dioxide, and you use the lion model, an example, and I think there could be other ways in which you can capture carbon dioxide, but you implied that probably there is just one way, and that is to allow the lion to escape from the zoo.
Okay, no, that was not sorry, but that was not how we meant it. We meant when the lion leaves the zoo, definitely it's going to cause havoc. That's more like what we call CO2 and gas flaring, and trying to.
Probably there are other ways in which you can capture this without necessarily saying that it must escape and that you are going to have to take care of it.
Okay, we are not saying it's going to escape. We are saying it's a closed loop within the system. While we are producing from your well, you are actually getting it from there, rather than allowing it to escape before you go to capture.
Is that your novelty? Have others not been able to try to do a closed loop capture?
Well, from the best of experience, and I have made a lot of literature review on the work, I've not seen any other company or any other person who is trying to work on the technology of trying to incorporate this technology, produce methane without the emission of carbon within the system.
So it's fine. I think I'm only trying to make a provocative comment to say that I'm not sure about that. I have some ideas on CCS, but I'm not sure about that example. And probably you might need to be a bit more careful in your claims and probably need to do some homework.
So I'll sandwich my response. I think you've put quite some effort in what you're doing. This is actually daring and very daring, and you shouldn't stop. However, a few fundamental things that may influence how you see this world. First, making methane is not what results in carbon emission. It's the combustion of the methane that has carbon emission associated with it. So, which is quite fundamental to what you did, because if I looked at your chemistry, you split the methane into, oxidize the methane, which is essentially combustion, into CO2 and into O, and then you make it back into methane, which is like your end product eventually, which when somebody else uses, you probably still get the CO2. So it's sort of cyclic. Okay, if you disagree, you can make a comment. Secondly, genetic engineering, I saw that in your statement. I wanted to get clarity on whether you are performing the genetic engineering or you are buying already genetically engineered organisms, which I don't think you can purchase within the limit of your $378. So those are things you really need to look at. But again, this is a very daring concept. Well done.
Thank you so much. Can we appreciate them, please? And give a resounding applause for all the presenters here. Please, can we rise and applaud all the presenters across 10 universities? This is a great job done here. Thanks so much. And to our judges, can we clap for our judges as well? For doing a great job. Okay, it's time for question goal. Can we proceed with the setup, please? Thanks so much for your time. Okay, as the press report setup is going on, the judges will be collating the scores for the energy challenge.
Yeah, this one.
Sorry, your head will not show.
You tell me to bend down now.